Hey, good morning, everyone. It's my pleasure to welcome you to this continuing series of colloquia on the celebration of faculty careers. Usually the lead-off or the introduction is by an associate dean. I think they are all unavailable today for some reason. So the pleasure and the privilege of introducing Mike today falls upon me. I'm very happy that I had a chance to do that. So what I'd like to do is to give you a brief background on what this colloquium is all about. So the celebration of faculty careers evolved from two actions of the strategic plan. It's the faculty of, one of them is the Faculty of 2020, with its focus on professional development at all stages, and the alignment of criteria and processes for hiring and promotion and tenure with the evolving scope of the college and its leadership values. A specific outcome approved by the engineering leadership team was that all full professors on a 7-year cycle will present a college-wide colloquium with the following two goals. One is to provide an opportunity for all colleagues in the audience to learn and celebrate the faculty member's successes. And the second one is to provide the faculty member with an opportunity to plan for the next phase of his or her academic career. So in that vein, this colloquium will be followed by a planning discussion with the dean and the department head.
I really look forward to that.
This was piloted successfully in spring of 2013, and full implementation, of course, began in 2013-14 academic year. So therefore, it's my pleasure again to welcome you all. Typically, this is followed by a long introduction, but in Mike's case, I don't think he needs any introduction.
Yeah,
Mike got his BS and MS degrees in EE with the highest of honors from Drexel in 1983. Got his PhD in 1986 from the University of Pennsylvania. Joined us immediately afterwards, and he is currently the Thomas and Wendy Engibus Professor of Electrical and Computer Engineering. Please join me in welcoming Mike.
Thank you, Miguel. Okay, I'll just get right into it because I got a lot of slides. I apologize. So what I do is called array signal processing, although the name has changed over the years, and I have a slide on that in a moment. Let me just go through this to get everybody in the same boat here. Array signal processing deals with the multidimensional processing of the signals received at a collection of sensors spaced at discrete points over some aperture in a multi-component signal wave field. Okay, and that's a very good definition, so I want to read it verbatim. These are the application areas that I worked in with the, this one the most, second most, and so forth, with the red here. I haven't worked in these very much, but these ones here. For the wireless communications application, what makes it challenging and interesting is multi-path propagation, reflections off buildings and other structures, and also co-channel interference, signals in the same frequency band. Okay? And everything I do, as I said, array signal processing involves multiple antennas, and I'm going on almost 30 years working in this field. And when I first started doing it, it was called antenna array processing. But you have to give it a new sexy name every so many. So in the 90s, when the wireless revolution was taking off, it was called smart antennas. And then somewhere around in this decade, or the past decade, I should say, they started calling it MIMO for multi-input, multi-output, when it involved multiple antennas. And now, 2010s, we have so-called massive MIMO. And all I want to say is that I was in the massive MIMO before massive MIMO was cool. That when I started working here at Purdue, these were already in play. These are huge phase arrays that one of them, this one I think is situated on the coast of Alaska. It was meant to monitor ICBM tests in Russia. And it has over 13,000 antenna elements on its face, 13,000. So massive MIMO has been around for a while, because now we have to move to we're moving to higher frequencies, so we're moving to miniature versions of these. I cannot go far into talking about my research without talking about eigenvectors and eigenvalues, and in particular matrix theory. Matrix theory plays a role in everything I do. There's not a day that goes by that I don't do something with matrices and vectors and eigenvectors in particular, and singular values. So let me just say, so when I was an undergraduate, you learned about eigenvalues. You solve this determinant equation here. Then you solve to get the eigenvalues. Then you solve this to get the eigenvector that goes with each eigenvalue. And if you write that this way, you realize that what's happening is that the subtraction of this lowers the rank, so there's a null space, so there actually is a solution. And if a lot of my matrices I deal with are what are called covariance matrices, and they are Hermitian symmetric, so the eigenvalues are real valued, and the eigenvectors are mutually orthogonal. If A is positive semi-definite, in addition to this, then the eigenvalues are non-negative and real valued. And I think I might have learned this in grad school, that this is maximized when the W vector is equal to the eigenvector associated with the largest eigenvalue, and that's the maximum value, is the largest eigenvalue. And it's minimized when the W vector is equal to the eigenvector associated with the smallest eigenvalue. And then I went to grad school, and I learned, well, you can have these equal generalized eigenvalues when what's up there is not the identity matrix. And I thought, oh, that's interesting. So these are generalized eigenvalues, and again, eigenvectors are solved this way, and again what happens is the subtraction of this lowers the rank so that there's a null space, and there's a solution to this. What I thought was really cool was that now you can have this definition of orthogonality where this B matrix was wedged in the middle. Now B has to be a positive definite matrix, and this is for Mark here. And then you can talk about working in a Hilbert space where your inner product is defined between x and y is defined this way, and that satisfies all the conditions for a Hilbert space if B is positive definite, and in particular the norm would be defined this way. And then I learned that, again, if you had this ratio, what we call quadratic forms, W is a vector here, an n by 1 vector, let's say. Again, let's enumerate the eigenvalues in this way. Again, this is maximized when the weight vector is the eigenvector associated with the largest eigenvalue, and that's the largest value of this, and also minimized when the W vector is the eigenvector associated with the smallest eigenvalue. And you might think like this might be the signal covariance matrix, and it must be the noise covariance matrix, and you're minimizing the signal-noise ratio. Okay, then as I got here at Purdue, I learned about Felix Gottmacher, a Russian mathematician. He wrote this book called Matrix Theory that was used all around the world. And he generalized it to, you don't have to have square matrices. So he had a case where these were just, rectangular matrices in general. And it's the same thing. It's just the subtraction of this lowers the rank to give it a null space. And I had a perfect application for it where the X were the snapshot from one subarray and Y were the snapshots from an identical subarray that was displaced in space. Let me get a little notation here. So let's say you had a planar array. At each of these points, there was an antenna there. And most of the time when I say sensors, most of the sensors I worked with are antennas. And so this would be what we call a rectangular array of sensors, rectangular array of antennas. Theta is the elevation angle that's down from what we call boresight to the array, perpendicular to the array. And then phi is the azimuth angle in this plane, 0 to 360. And theta goes between 0 and 90. And you might take, like this might be your first subarray. And then the other one might be this one. It's an identical subarray just displaced along this axis. And you might go, then the other one, you might go take the one subarray to be this one. And then this next one to be this one, just slide over one element. Okay, in those situations, we form these Y and X matrices from what we call snapshots. Snapshots are simultaneous sampling of the output of each of these antennas after they've been mixed down the baseband at an instant in time. And we put the snapshots as columns of Y for the one subarray, and as the columns for X for the other subarray. And what you show is the eigenvalues here are directly related to directional information. That's the wavelength associated with the center frequency of operation. D is the spacing between the antennas. And this is the direction cosine with respect to the displacement axis. And in particular, what happens is, let me get a little array processing 101 here. When you have a plane wave incident upon, let's say, a linear array of antennas, and it comes in at an angle, this ray, that same point in the plane, to get to that, it travels a little extra distance to get to this one here. And it's dependent on the angle theta and the distance between the antennas. And that causes a time delay. And I should have put this in the slides. At these very high frequencies, usually you have some information portion of the signal. And that time delay, as you go across the array, as long as this condition is satisfied, that time delay on the information portion of the signal is negligible. But at that high carrier frequency, that time delay causes a phase shift. The product of the carrier frequency, which is very high with this very small time delay, might be the order of nanoseconds, this might be the order of gigahertz, that's significant. But the time delay for the information portion of the signal is negligible. So in the end, what we get is this phase progression across the array that depends on the angle of the incident of the plane wave. And it looks like a discrete time sine wave, except we call it a discrete spatial sine wave. Right? And where this mu, again, is the 2 pi over the wavelength, the inner element spacing, and the cosine of the angle. And the Nyquist spacing for antennas is half wavelength. And if you use that spacing, then you have pi cosine theta. Cosine theta goes between -1 and +1, so mu goes between -pi and +pi. And if you look at this and you define z this way, it has what we call a Vandermonde or polynomial structure. and so allowed for routing-based schemes to determine the angle of arrival of multiple plane waves incident upon an array. Okay, and that's important for something I want to say later. So I said, oh, I have a perfect application where my X matrix looks like this, my Y matrix looks like this. The A sub k is a column vector, it's that what we call directional arrival vector. And the S is a row vector when it's transposed, so that it contains this information portion of the signal, and it's a row vector. And the only difference between these two, because that displacement is this phase term due to the displacement, and again, it depends on the angle of arrival. And so I realized, oh, I have a perfect matrix pencil where the eigenvalue will give me directional information. And it turned out that because of the orthogonality, the wave vector you get with it is what we call a beamforming vector that nulls out the other sources. That is, let me show you a picture. Like, let's say you had two sources, two plane waves incident upon the array at these angles. Spatial frequency is synonymous with angle. And one is in this direction. And then so this one would be lining up with the peak of that one. And so if you just applied this standard beam, you would get both signals coming through. And this is only 13 dB down, and you get interference. But what that wave vector does when you compute the eigenvalue and find the associated wave vector, it actually puts a null on the other source. See that? It put a null there. And it automatically did that. So this was a pretty cool application I had. Now, along the way here, I want to tell some stories. So this was my first summer here at Purdue. I spent it at the Naval Ocean Systems Center in San Diego, which is now called Spay-War. And the people I worked with there, they said, you got to read this book by Goldman Van Lowe called Matrix Computations. You'll love it, you know. And they told me, I learned about the QR decomposition, and that whole summer I just ate it up. And in one of the last chapters, I don't know if it's one of the last chapters now, but they had this thing called the Procrustes rotation problem. And it said, if you had, this was one basis for some k-dimensional space, and this was supposedly, at least theoretically, a basis for the same space. But because of noise and other factors, they're not exactly the same. And so you want to find the best unitary matrix that rotates this one into that one. And they had an SVD-based solution for it. SVD stands for singular value decomposition. And I never thought I would use it, but it turned out I had a perfect application for it when I went ahead and tried to combat the effects of noise by doing rank truncated singular value decomposition for both the X and Y matrices. And I realized that these things, if it wasn't for the noise, would have the same range space, and same thing for these, the V's. The U's would be the range of those A vectors, and the V's would be the range space of the S, the signals. Anyway, so I had a perfect application for the Procrustes rotation problem. And if I could say anything to the grad students in the room, that you just soak up any math results that you can, because you never know when they may come in handy, and I'll make that point again later. So using this, and I'm going to gloss over the mathematical details. Using all this got me down to a regular eigenvalue problem, k by k, where k was the number of incident plane waves, where the eigenvalues again gave me the directional information I was seeking. And this led to my first paper award. And by the way, so when I was trying to think of what to overview today, I've been working, like I said, 30 years in this area. The best decision I thought was to just go with the work that got honored with paper awards. I thought that was the best way to distill everything I've done. So this is my first paper award. It was on this paper here. And so to tell a story, I forget where it was, but anyway, at the award ceremony, I sat next to Mark Smith. He was at Georgia Tech at the time. He's now the dean of our graduate school. He was the head before at Ragu. He was getting a paper award. So he was there getting paid, and we sat next to the other table. Jan signed my certificate, because he was secretary for the signal processing side at the time. And our dean, Leah, was the vice president for awards. And she handed me the award. So that was pretty cool. And to tell the story further, later on, I was elected secretary of the Signal Processing Society, and later I was elected to be the vice president for awards and membership as time evolved. So, okay, come on in, you guys. We'll sit down, plenty of seats here. Okay, so I want to highlight a couple more pieces of work where I use the matrix pencil concept. And so there was the second generation cell phones. It's based on the IS-136 standard. I don't really come up with these numbers, but whatever. And it was a fairly basic pulse amplitude modulated signal. And I realized if I took the magnitude squared of that, which is this, the expected value of the magnitude squared, I'm sorry, which you get through time averaging, I got something that was periodic with period t, the symbol rate, 1 over t is the symbol rate. And I was teaching 301 at the time. I said, well, I can talk about a Fourier series for that. And it turns out that with the pulse shape, the square root raised cosine pulse shape that was used, there was only energy at DC and energy at the symbol rate and no other terms. In fact, the only reason there was energy at the symbol rate was because of the squaring. There was no energy at the symbol rate without the squaring. So again, glossing over the mathematical details, that motivated me to form these two matrices here, where that modulation there is essentially the digital frequency version of the symbol rate. If you sampled L times the symbol rate, it's your sampling rate. And L equals 4 was a good idea. And it turned out again that when I looked at the eigenvalues and eigenvectors, the generalized eigenvalues and eigenvectors of that matrix, pencil, it gave some very useful information. In particular, the eigenvalues giving timing offset information. That is, relative to the time you called t equals 0 before you had any synchronization, you would get this eigenvalue that went between minus all around the unit circle, and it would tell you the close from what you call t equals 0. It would tell you the nearest point where you had no inner symbol interference, where the eye diagram. Anybody who does communication knows these eye diagrams. It would tell you the point where the nearest point where there was no inner symbol interference. This point here, from the point you call t equals 0, and that's just for BPSK. This is for Fourier signaling. I just grabbed these from the web. And it was not quantized. It was not rounded off. It gave you the actual absolute time from what you called 0. Even though you had sample data, it told you exactly where to find the closest inner symbol free point. Okay, and that was cool. And then once again, it's the associated eigenvector, the one with that eigenvalue for that particular source. And again, this is for multiple co-channel sources. I should say. This is for multiple co-channel sources. Not a lot. This is for a cellular situation. So you might have, maybe they allow, we're trying to allow them to have space division multiple access, allow multiple people to be in the same sector in a cell and overlapping in time, totally overlapping in frequency. But if they were at different angles, we were telling them, hey, we can beamform and we can grab the one source, we can null out the other source. And sure enough, that same eigenvector is what we got before. It would point to one source and nullify the other source. And so now it was a great solution. The problem back in those days was, and it's still somewhat of a problem, but we're in the 5th generation, which we'll talk about later. Hopefully we're moving to overcome this. But we could have multiple antennas at the base station. Everybody's willing to pay for more infrastructure there and have maybe 3, 4, 8 antennas at the base station. But your cell phone typically had one antenna. And maybe a laptop might have more than one. But back in those days, there was an imbalance between what you could do on the uplink with multiple antennas at the base station versus what you could do in the downlink, and the cell phone or smartphone only having one antenna. So it took a while for these things to get adopted because of that imbalance. But this led to another paper award. It was at the MILCOM conference in 1998. I'm dating myself here. And it was for the best paper in the unclassified technical program. And both my student and I received the paper award, and that was quite an honor. Okay, then I had a student from Spain write me at the Polytechnic University of Madrid, and he had an advisor who wanted to build an antenna array, and it was going to be a circular array, and he wanted to have it tuned so that it operated around the GPS signal, so that they could use the GPS signals as signals of opportunity to do experiments and so forth, because they're out there, and always on. But he said, he wanted to do a dissertation that was more, the signal processing. This advisor was, I guess, probably just more an RF person. I'm not sure, but he really wanted to do signal processing, but the advisor was going to fund him to come over and work with me. So in the end, in his dissertation, there was one chapter on building the antenna array, but the other 4 chapters was the work we did. And I explained this the thing I just talked about, which won the award at MILCOM. I explained that whole idea to him. And he had the idea, well, we could apply this to rather than TDMA, the standard. He said we can apply it to the CDMA standard by first, again, I don't want to gloss over the details, but first running the correlating with the pseudo noise sequence that a user was assigned with sliding over the delay spread 1 chip at a time, or if you want to sample at higher rate, you could slide over half a chip at a time if you want to make sure you don't miss a dominant spectral multipath. And then, again, to gloss over the mathematical details, we can get eigenvalues that told you what the relative delays were of the different multipaths that were, coming. They come in at slight, right? They have to bounce off buildings, so it takes longer before it hits your antenna array. So it will tell you the relative time delays, again, without being, it wasn't quantized. It would tell you exactly where the time delays were of the dominant spectral multipaths, and gave you a beamforming vector that allowed you to extract that particular dominant spectral multipath, and so you could add them up and get actually a signal noise ratio gain. So he ran with that idea, and in the end, His dissertation back in Spain was awarded the Erickson Award for Best PhD dissertation in the area of mobile communications in 1995 by the Spanish equivalent of our IEEE. And that was cool. All right, another piece of work here. I had this idea of doing equalization for the forward link in CDMA. Forward link is when the base station is communicating into the cell to your cell phone. And I had this idea that to do equalization. Okay, and it turned out that we found out later, at least a year later, that there was a researcher at Motorola that had the same idea. And usually you're disappointed when somebody else had the same idea around the same time you did so. But I actually was quite happy about that because this idea of doing equalization for CDMA was, well, I'll say, outside the box. The selling point for CDMA was that multipass would be resolved in time and then combined via rate receiver, kind of what I just talked about for enhanced SNR. But the reality was that the base station, when broadcasting in the cell, had the luxury to line up the users. Like the users themselves were at different points in the cell, and so they came up to on the uplink. They came at different time delays and so forth. But the base station had the luxury to line everybody up before it broadcasted into the cell. So they decided in the standard to use orthogonal watch-Hadamard mark codes, which makes a lot of sense. But when there was multipath, these had very poor autocorrelation properties, and we'll talk about autocorrelation later on in our little talk here today. And the end result is that that the multipath propagation, the reflection off buildings and other structure, really destroyed the advantage of using the orthogonal watch-Hadamard codes. So the idea, well, why don't we do equalization to restore that original transmitted subsignal to get us back to having these orthogonal codes that were lined up and you exploit the orthogonality. I was happy to learn that somebody in industry had the same idea because I thought somebody else said, this is just some crazy academic person come up with this crazy idea. That our serious research in industry at Motorola had the same idea. And so, and we, relative to a rate receiver, we had dramatic improvements in performance. And I'll show you those in a moment here. So this is basically pulled right out of the standard and use these watch-Hadamard codes on the downlink. And the one thing we always did in our work was we included the long code. That is, there was a lot of work at the time, people saying, oh, if a person kept using the same code from one symbol to the next code, there's a lot of great things you could do. But the reality was that in these CDMA systems, at least the commercial ones, and they had this thing called a long code. There was a base station dependent long code that didn't repeat for days or something like that. And they had a user long code, and these did not repeat very often. So we always factored in the long code into our work, and we made our work more practical that way. All I want to say on this slide, once again, that things I was teaching in 301 at the time, came in handy in enhancing the research I was doing, amazingly. So again, what we're having, we were considering the problem of soft handoff. In CDMA, one of the selling points for CDMA at the time, I'm giving you history here, was that for TDMA, when you were switching from one base station to another base station, you're driving up I-65, and you're getting far away from this base station, now the other one's going to pick you up, you had to be moved to a different frequency band. One of the selling points for CDMA was because there was more frequency reuse, you could do the same frequency band in the adjacent cell because you'd be assigned a different code. So you had the so-called soft handoff. You could stay in the same frequency band. Okay? But the reality was that then at a certain point they were interfering at the edge of the cell. So this idea of doing this so-called equalization for CDMA was even more handy. And so we were talking about having two antennas. We're hoping that eventually we'd have two antennas on a smartphone or something or a laptop. And doing equalization at the two outputs to get us back the original transmitted signal. And then once per symbol, you had N sub C chips per bit. That was the length of the code. You would correlate with your code, and because you were talking to everybody else, everything worked perfectly. Despite but there was noise, obviously. All right, but then I looked at this and I said, well, this is an LTI system in series with another LTI system, and convolution satisfies distributed property. I can bring this and put this back in here in series with that one, in series with that one, and of course we know then once they're in series we can convolve their impulse responses. I know we're good at 301 as well. And I said, I can combine them down to another, just into this structure here, where I would constrain these things to lie in the space of slid over versions of this, if I want to put it that way, of this thing here. Delayed versions of this. Sort of a convolution structure anyway. And this actually improved performance, as we'll see here in a moment. So my only point is that even things I teach in undergraduate help my research. And this, again, was, I'll show you some performance curves in a moment, but again, this was honored with a paper award, this work at the IEEE International Symposium on Spectrum Techniques and Applications. This is work I did with Tom Krause, and Tom was a great student to have here, and he's working with us still. He was working at Motorola for a while, but now he's at a company called, anyway, they're trying to, we're working with some product called Sidekicks, I remember that much, that he's giving us for free, that we're going to, I know Jim Krogmark's involved in that. And just again, to show you, even if we had a lightly loaded cell, that is only maybe 8 of the 64 codes, they use these Watch-Heidelberg codes, only 64, were being used, we had an advantage over using a rate receiver. But the minute you had all the codes being used, which is what you want, right? You want to be able to handle a lot of users, and you want to even be assign users more codes, because you assign them more codes, they can send more data at the same time. Here's a rate receiver. The rate receiver just, wait. The name of the game here is to get these things to bend down as quickly as possible. This is signal-noise ratio. This is bit error rate. So you want these things to bend down as quickly as possible. And the rate receiver in that case was just, it just saturated. It was awful. It was 10 to the minus 1. So, but yet these, the chip level equalization got us down to here. And then the symbol rate, the other thing which I use 301 material, bend it even further. So I guys want to say that even 301 material comes in handy every now and then, even in this high-level research that I do. Okay, this work here was very important to me, and I think it was my understanding was a large selling point when I went up for nominated for the Technical Achievement Award, which I'll talk about in a moment. I talked about earlier that if you had a linear array, I don't know if I have a picture here, you could ultimately pose the problem of finding the angle. I only show one plane wave incident here, but we generally have multiple plane waves incident upon the array, and we'd like to find the angle arrival of each one of them. And because of this phase progression here, and if the elements are equally spaced, I showed that structure earlier. It had a polynomial structure to it, and so you could pose the problems of finding those angles of arrival as a rooting problem, the roots of a polynomial. Okay, without again going into all the details. Okay. But no one had to know how to do that but all that gives you, by the way, is the angle of the plane wave relative to the axis of the array. And if you think about it, if you have, if you take a line like this and you rotate it around the axis at the same angle, you get a cone. And what I'm trying to say is that different sources at different locations, if they were on that cone, gave rise to the same angle of arrival. So what you'd really like to have is a two-dimensional array, like a circular array or a rectangular array, where you could get both azimuth and elevation, and not just this conical angle of arrival, which didn't really tell you a whole lot. Now, if it was like, lying on the ground, and if you were sure your searches were like boats, so you knew they were a certain, then they could give you useful information. But generally speaking, you like to have 2 dimensions and be able to get to both azimuth and elevation. And again, elevation is theta, which is measured relative to the boresight, which is orthogonal to the plane of the array, and that goes 0 to 90. And then azimuth is 0 to 360 in this plane here. So no one knew how to do, there was a lot of nice features to this routing structure, because otherwise you had to create what we call a spatial spectrum, which supposedly as a function of azimuth and elevation, for example, and it would show, hopefully large peaks where there were sources, and hopefully be small away from there. But the reality was it was all kinds of garbage. Okay, it was a multi-dimensional search over a multimodal surface. So if you could come up with a routing technique, it would be a big contribution, and I came up with one. And ultimately, what I came up with was an algorithm that it was eigenvalues again. And eigenvalues are the roots of a polynomial, right? The characteristic equation. I came up with an algorithm that for each co-channel source gave you a root, an eigenvalue that looked like this, that the magnitude of the eigenvalue was the sine of the elevation angle. If theta equals 0, that was boresight, it would be right here, sine of 0, 0. If the theta was 90 degrees, that the source was in the plane of the array, then theta would be 90, and it would be on the unit circle. So the magnitude tells you the sine of the elevation angle. And then the phase was the azimuth angle. No 2 pi over lambda. The phase was the azimuth angle. And so it gave you, for every root, it gave you an eigenvalue. I'm sorry, for every co-channel source, it gave you an eigenvalue, and the magnitude gave you the elevation value, and the phase gave you the azimuth angle. And that was pretty cool. And what I want to say is, well, I want to tell the story about this in a moment. So I did it first for circular array, and later on I figured out how to do it with rectangular arrays. But I want to tell both stories, so let's just talk about the circular array because I did it for that first. What we found is if you take a circular array and you excite it with a row of a DFT beamformer, a DFT matrix, and I know not everybody knows what that means, but just bear with me. You got, for every row, you excited it, it was called a phase mode excitation. You got this. And let me skip to this for a moment. So basically, once you excite all these different phase modes, you got the kind of structure I had earlier. There's this linear phase progression relative to the azimuth angle, but you had these Bessel functions in here. And I had no idea what to do with them. Okay? But again, this is advice for some of the grad students in the room. I used to just sit around in the old days, and I had this book, The Handbook of Mathematical Functions by Abramowitz and Sagan. And sometimes I would just read it for no reason, thinking someday I might use that result. And luckily I remembered there was some recursion that Bessel function satisfied. So I opened up, by the way, it's a free download for the grad students. It's a free download now. I remember this, so I looked up that Bessel recursion and said, okay, I wonder if I could use that. And sure enough, the answer is yes, I could use that. And in the end, using that in conjunction with this algorithm called a spree, I was able to come up with a way to set this all up so that, again, I'm not going to go through all the mathematical details. These are actual slides from when I used to give the talk way back when. But I did at least colorize it when I pulled them out. But in any event, here's the story I want to tell. And my wife remembers this. I had this idea in the middle of the night. We had triplets. And when they were quite young, one would be screaming in the middle of the night. And all you could do was get them. And you didn't want to have any TV on because you didn't want any stimuli. You just want to get in the rocking chair and just rock them back to sleep. You can't fall asleep yourself, or you've dropped the baby, right? So all I could do was just think. And just sat there in the dark thinking. And this idea all came to me, honest truth, came in the middle of the night. I'd already looked at the Bessel function recursion. I was trying to think, I bet there's some way I can use that. And all this came to me in the middle of the night, was how to do this and get out, again, for every source, you just set up a set of system equations. You get the eigenvectors of some covariance matrix. You form a matrix equation from that eigenvectors. And I know I forgot to move that hand out of the way. I apologize. Please move over here. Okay. Sorry for that was there through the other talk. And ultimately, this is the matrix equation. Rather than this being a vector, this was a matrix equation. You solved for a matrix. In any event, you took the eigenvalues of that matrix, and they were of the form we just talked about. So anyway, I thought it was a cute little story. It happened to be in the middle of the night. Okay, and then this is the run. We have 200 runs, just showing you a sort of scatter plot for two sources that were relatively closely spaced, at least for this particular array. There was only I think it was only 15 elements, I forget, but these were relatively closely spaced, and yet it totally resolved them. And this is 200 runs overlaid, and very tight scattering plot here, at least a 10 dB SNR. And what we said, by the way, use those to start your spectrum. Now you have this two-dimensional spectrum with multimodal, all these bumps on it. But you knew then where to start a search, and you could lower it and then do a little search around that area, and then you could get very close to the Kramer bound. Okay, that's that story. Another thing I worked on was with E-Systems, a fellow named Tony Geekin came to me, and they were worried about protecting GPS from jamming. Okay? And what they had were they produced all these circular arrays with an element in the middle. And what they would do is they said, okay, this is a preprocessor prior to the GPS unit. So it was totally independent of the GPS. It fed a signal into the GPS unit. And the idea was to try to say that, put nulls at the directions where jammers were coming from. And what would they do is they would set the weight on what they call the main antenna at 1, and then they find the weights on the other antennas so that when they summed everything together, find the weights that minimize the output power. The assumption was that the GPS signals were below the noise floor. So anything that would be null, that would be a jammer. And you get something like this, something that was fairly flat in general, because you want to get the GPS signals, but wherever there was a jammer, you would get a null. And depending on the strength of the jammer would dictate the depth of the null. And that worked pretty well, but they were doing, here's a picture, but they were doing something very simple. They would look at this antenna here. They did what was called coordinate descent. They would do one antenna at a time. They had this pattern for jumping around. And they would just diddle. They would say, okay, I'm going to diddle the real part of this weight and see if it lowers the power. If it does, then I'll keep it. And then I'll go to this one and diddle the imaginary part and see if it lowers power. And I was amazed it ever worked, but it did work. So they came to me, they were competing, and they say, can we make this faster? And so, yeah, we did a lot. I'm not going to go into the details, but we did a lot to speed that up and get the nulls to happen more quickly and so forth. So In that paper, we submitted that to the Institute of Navigation Conference, and that won the E-Systems Best Paper Award. Then another paper award, I had the student Tyann Chen, and I was supporting, and I wanted to collaborate with Mike Fiss, who was here at the time. And I was like, well, you know, so we have to deal with multipath propagation, reflections off buildings and other structures. And there was this thing called Jake's model, you know, been around since forever, and assumed that around the unit, the mobile unit, was this circular ring of scatters that were essentially equally powered, you know. And you could get some insights from that, but you know, we all know that wasn't the real world, you know. So you know, I sort of tasked Tyann with looking at, you know, let's try to develop more real models for that, and you know, and maybe they'll be, you know, dependent on the surroundings and something like that, so forth. We can have different models for different scenarios. So Tyann was a really good student, and I've been blessed with many good students. And he went to task, and he collaborated with Mike and I. It was a great collaboration. And he came up with you know, space-time models for non-selective Rayleigh fading channels. And the one thing he also worked on was, you know, for different models, what was the right interleaver depths for when you had to design your error control coding. So ultimately, that got published in this journal here, and that was a nice surprise. We got a paper award from the Communication Society, IEEE Communication Society, and that was given to us at ICC in Helsinki, Finland, and that was pretty cool. All right, then all that ultimately led to the Technical Achievement Award, which, you know, it's one thing you dream of getting, and then I never really thought would happen. And out of the blue, I get the, I think I was aware I was being put up for it, let's just say that at least. And that was at ICAP 2003 in Hong Kong, and I feel very blessed to have gotten that. Now I want to tell some stories that aren't paper awards, but highlights of my career. You have to understand, and Mark will appreciate this. I mean, when I was going through grad school and early professional years, Harry Van Trees was a god, okay? I mean, he had written this, this multi-volume series, volume 1 and 2, on detection and estimation theory. And everybody in our era, that's where we learned detection and estimation theory from Van Trees' book. So he's like a god to me. So then I didn't meet him until probably at least 10 years after I'd been here. I met him, I think I was working on a DARPA grant, in fact. And when we got introduced, he said to me, here's the sage of Indiana. I was like, whoa, wow, what? He had been reading my papers, and he told me he included a lot of my work in the 4th edition of his series on detection. This is volume 4 of his series on detection and estimation theory. And ultimately, he gave me a free copy of the book where he inscribed, and I have it written here, you know, it says, I admire your many contributions to the field. And all I can tell you, that coming from Harry Van Trees was greater than any paper award. So that was definitely a highlight of my career. And that's me with Harry there. Irving Reed, another amazing giant, you know, person. I knew him mostly for his work on Reed-Solomon codes. Reed-Solomon codes were used for everywhere. And actually, there's a very interesting story of why he developed Reed-Solomon codes. It was for D-space communications. And so when I met Irving, and I gave a talk one time at USC, and we talked everything. And so then we kept in touch. And then, just to tell a funny story here, I was invited to his 75th birthday celebration. And I was at, it was going to be early November, and I was at a conference, called a Silomar that was up in Monterey. And I said, oh, it's perfect. When Silomar ends, I'll fly down to LA and USC, and I'll go to his 75th birthday party. So I went there. I didn't get to talk to him when it was all said and done, and he had like a receiving line on the way out. And when it got to me, my turn, he said, okay, where'd you come? What's going on? I said, well, I was at Silomar. I flew down here. And he said, well, why didn't you give us a talk? And that comes from Irving Reed. And here he's his 75th birthday. He's upset that I didn't come and give a talk at USC. That made me feel really good, like he respected my work. You know? Anyway, that was another highlight. And that's me with Irving Reed there and his wife. So, okay, I just want to tell some stories. Around the same time, this is something you dream about. Maybe someday you'll be honored by your school that you went and got your degrees at. And I got the equivalent of OECE, Distinguished ECE Alumnus Award from Drexel University. As Raghu mentioned, I got my undergrad at Drexel and my PhD at the University of Pennsylvania. And I went to school in the city where I grew up, so my parents were still there, my whole family was still there. So it was a great thing to see some of my old professors, and Carla was there, and my whole family was there. So this was another great honor. So then ultimately, the reason I'm talking today is yes, I was very honored to be awarded the Thomas J. and Wendy Engibus Professor of Electrical and Computer Engineering Endowed Chair. And I have a strong relationship with TI, and Tom Engibus got both his bachelor's and master's here. And then he went on to eventually become president, CEO, chairman of the board, everything, all those things at Textured Instruments. And then he retired, and last I heard, but now he's doing something with JCPenney or something. Chairman of the board of JCPenney. So. Okay, I want to talk about the MURI for a little bit we had. It ran for 5 years, and we interacted with all these universities. I got to work with Mark, which was great. He's the true sage of Indiana right there. And another great thing, I got to work with Robert Calderbank, and at the time he was at Princeton, and then eventually became the Dean of Science at Duke. And one of the greatest things that came out of it was interacting with him and working with him. A really smart gentleman and a very honored gentleman. And so we still have this is a website where we reported all the materials, and it's still up and running, and things are all posted there. To talk about this work, I want to talk about multidimensional matrices. It's an easy way to talk about it. So it's like, this index will be time slot, which will be like pulse repetition interval in a radar case. And then this index will be signal index, although it could be what different signals being transmitted from different antennas. Okay, but definitely it's going to be signal index. And then what's contained along this dimension is the signal itself. Okay, so it's a three-dimensional matrix. And MATLAB, you can do this. You can do any dimension in MATLAB, and we'll talk about more dimensions in a moment here. So, and then so in these three-dimensional matrices, I'm going to define, and then maybe somebody defined this along the way, but I'm going to put a convolution here. And what I'm saying is that between these two matrices, when you multiply, we all know about matrices, you multiply this into that, this goes with that goes with that. But instead of pointwise multiplication, it's convolution instead. Okay, that'll help me to talk about some things. So replace the pointwise multiplication by pointwise convolution. And again, you can think of these as outward from the wall here, that the signals are, this is a signal. And it's elements, it's a discrete time signal. And it's just contained in this dimension. Okay, so for the people I feel sorry for the people that don't have these mathematical backgrounds and have to list all this mathematical jargon. I threw a couple pictures in here. This is the old style radar. It's swept around like this, rotated there. But ultimately, this still is useful, don't get me wrong, but most of them are replaced by phase arrays, where you can steer the beams without actually having to physically rotate the antenna. And the kind of things you can get with radar. I remember, and unfortunately, one of our alum got all 3 of his degrees here. Jack Jakowitz just passed away, but he worked for Sandia Laboratories, and he said, Mike, if you can get your clearances passed out there, also things will make your eye pop out. When I was giving this talk at some other places, I wanted to add a little bit of humor, so I Googled funny radar pictures. So these came up. Speed limit enforced by aircraft. This came up. Camels, but a radar thing. A synthetic aperture radar in your own backyard. So Google's great. All right, so I just a couple slides on evolution of radar. I talked about the sweeping in azimuth, old style radar, we rotated. And then the second generation, you could say it was, they didn't even call it second generation, but we called it that. And with space-time adaptive processing, where you would try to get rid of reflections off the ocean or any kind of or the ground. We call it clutter. And also get rid of interferers, space-time adaptive processing. And then as we moved on, radar became MIMO as well. Not just, it was always multiple antennas, but like maybe multiple apertures. And then, we hope that we can use waveform diversity. That's what the whole idea behind the radar was, the MURI was. Well, swimming has been a large part of my life, so I had to find a way to throw it in here. I have a son and daughter that swam from like 8 or 9 years old up till the current time. My son swam from Michigan State. My daughter swam from Michigan. And so I had to throw that in here. And it actually was useful for an analogy here. This is at one of the meets. I think, okay, between radar and swimming, you can look at, what we're trying to estimate is the round-trip delay between the radar and the target. And that's like the 50 free. You go back and forth once in the 50 free style. Pulse repetition intervals are like multiple heats of the 50 free. That's a little loose combination here. But this is the best thing I could think of. That I want to figure out, if let's say I have multiple emitters, that I can transmit multiple waveforms simultaneously from different emitters. They might be different apertures, different subarrays of the overall array. I can emit multiple waveforms simultaneously over multiple pulse repetition intervals. What waveform should go out of what, let's just say antenna. What waveforms come out of what antenna at what pulse repetition interval? And that's equivalent to if you had to field let's say you had to field 4 relay teams, each relay team in the 400 free, let's say a 200 free relay. Each one has to swim back and forth once. You have to decide, let's say you're fielding 4 teams at the same time, 4 relay teams, 4 different lanes. You have to decide which person goes in what lane during what leg of the race, like the beginning, the 2 middle, or the final leg of the race. I feel that's an analogy here to what I have to do with the radar problem and scheduling waveforms. So I had to find a way to put swimming in here. And this is the case where the relay teams were being set up here. Now, what are some differences in the course? The speed of the swimmer is unknown, whereas we know the speed of electromagnetic waves, that's the speed of light, ideally, at least in free space. And of course, there you know the distance between the blocks and the far wall, but in radar, that's the thing we need to estimate. And the biggest one is this, that the swimmers stay in their lane. But once the radar the signal reflects off the target, it comes back to if you had multiple antennas that were transmitting, it received at all of them. So they got all mixed together. It didn't matter that they were standing from different antennas to begin with. They were all mixed together when they came back. And that's what makes it challenging. Okay, radar 101, or at least pulse compression radar 101, and even chirp radar form. That if you have a signal that you send out, a known signal, and it comes in at different delays with different scalings on them, one of the best ways to, actually no, not the best ways, but one of the most common ways to try to estimate those delays is to run the received signal through a match filter. And the match filter is simply the signal you send out, which you know what it was, flip it around and conjugate it if it was complex value. And if you do that, what happens is wherever there was a delay, you get what's called the order correlation of the waveform you sent out centered at that delay. And so you want the order correlation to be this spiky looking thing, like to be a delta function as best as possible. So here's something I use an example in 538, the course I teach. This is the signal we sent out was the PN sequence, signal plus and minus ones. There are two delays embedded in this signal, but you can't see that at all. This is what you received. But because of noise and also the fact that the order correlation isn't perfectly a delta function, but mostly because of noise here, you can't see that. But when you run the match filter across this data, you get nice peaks due to the order correlation. This was a fairly nice delta function, though it had what we call a side lobe, so if you want to call it that. So it easily comes up, and there's this blowing of that. All right, so you cannot design a single sequence of plus and minus ones. You cannot design a sequence of plus and minus ones for which the order correlation is a delta function. And why do we care about plus and minus one sequences? It's because we have to operate the amplifiers that we use in the nonlinear mode. To get the most bang for our buck in terms of energy out for energy in, we operate the amplifiers in the nonlinear mode. And so if we had different amplitude levels, they would get distorted. So that's why in radar and even communications, there's a lot of interest in things that are what we're called unimodular, meaning that it's either a plus one or minus one amplitude. Because really, it's a sine wave. We ultimately take the sequence of plus and minus ones and multiply them by high frequency sine wave. But anyway, so you cannot design a single plus and minus one sequence for which the order correlation is a delta function, but you can design two sequences of plus and minus ones for which their order correlations sum to a delta function. Okay? And those common examples are called Golay pairs. So we had this idea of, okay, we'll transmit the Golay pair out of, let's say, transmitter 1 or emitter 1, and we'll transmit the other one out of transmitter 2 at the same pulse repetition interval. And then the next interval, we'll take this one, transmit it out of here. This is, again, the three-dimensional matrix. And we'll take this one and turn it around and conjugate it, and take this one and have it come out of transmitter 2. And now this one that came out of antenna 2 come out of antenna 1, but turned around and conjugate it with a negative sign. And it turns out when you run the match filters, this is done for each receiver. When you run the match filter tuned to this one and the match filter tuned to that one, and now sum them together, for transmitter 1, you will cancel all the returns from transmitter 2. You'll isolate only what transmitter 1 sent. At the same time, you're getting the delta function effect. And the same thing if you tune to this one, match filter, and tune to that one, sum together, you will only get what came out of transmitter 2. You'll cancel what came out of transmitter 1. At the same time, you're getting the delta function effect. It was a really cool contribution. And I can't take total credit for that. In fact, Robert Calderbank and some other people came with that, but they let me run with it. And I designed it for 4x4 and came up with other ideas for how you design these sequences. So then to generalize that, we had these matrices that, again, this is a three-dimensional matrix. This is that convolution operation. And this is the matrix match filters. To make a long story short, that again, what's happening is, let me go to the slide here. This is what we designed to satisfy this. And what's happening is, again, along the main diagonal, we're saying is we can't design sequences of plus and minus one, a single sequence for which the order correlation is a delta function, but we can design multiple sequences for which the order correlations sum to a delta function. That's why you get the delta n along the diagonal. At the same time, we can't design two different plus and minus one sequences for which their cross correlation is 0 for all n. But we can design multiple sequences for which the cross correlations sum to 0. And that's what's really happening here, if that makes any sense. Again, if it doesn't, don't worry, just tune out for a minute. All right, so just an example, I won't get into that. To make a long story short, these are the kind of pictures we get. We could keep doing this over and over again and have different sequences you send out. I had lots of designs to try to get diversity, waveform diversity. And of course, what we want to show is that what ours compared to something else. And this is a 4x4 scenario versus a 1x1 scenario. But I did make the total transmitted power be the same, so it was a fair comparison. And there were 3 targets, 2 at the same Doppler at different ranges, and then another one at a different Doppler. And you can clearly see them delineated here. Very low background. Again, blue means very low amplitude. Dark red, very large. And if you use this was not a bad sequence. Not a bad sequence I used here to compare it against. Same length and everything, but I used it over and over again, and it's a complete mess. You cannot really see there were 3 targets there. So there was a lot, and this was on a dB scale. If you went on a linear scale and did a mesh plot, you can clearly see those 3 peaks. And here, it's a mess. Okay, so, all right, we're getting to the last phase of the talk here. I'm going to take that work that I did for radar and try to use it for communications. This picture has nothing to do with anything other than I thought it was a cool plot I found on the web. And it balanced out my little quad chart here. So, direct sequence spread spectrum. So now I want to spend, well, I guess whatever time I have left, if you let me go a little over. I want to talk about the future of my program. And that focus is on 5G, the next generation of wireless communications, cellular communications. And that's going to be at millimeter waves, and it's going to involve massive MIMO. Most people believe there'll be a combination of massive MIMO with millimeter wave. Massive MIMO might be small, but when you get those very high frequencies, the antennas can be very small. And direct sequence spread spectrum was you took a signal and you multiply it by a sequence of plus and minus ones. And this looks like an example of maybe something, maybe like 10 chips per bit. Here's the bit here, and then these are the chips in the middle. And when you did that, it spread the signal out. Okay. And then at the receiver, because once you synchronize, because plus 1 times plus 1 is plus 1, and minus 1 times minus 1 is plus 1, you would simply multiply by the sequence again, and that would spread the noise out and build the signal back up again. And you got this gain, which was equal to essentially the ratio of the transmitted bandwidth over the original bandwidth. You got a gain in signal ratio equal to that. Now, that's really cool and everything, but I always thought that you don't have a lot of control how the energy is spread. Okay, you just hope it's spread out, but you really don't have a lot of control over how the energy is spread. And let me just jump ahead here a second, and we'll come back to these slides. And because I know we're running short on time here. If you look at this picture, if you get to these millimeter wave frequencies, you start to have to deal with atmospheric absorption. So you try to operate around these sweet spots, okay? Like here and here, like 60 gigahertz is one of the areas people are looking at, communicating at. You try to operate these sweet spots. And so I feel like due to frequency-dependent atmospheric propagation, and other factors, and I like to think in the future we'll know maybe something about the channel. We'll get some feedback. I would like more control on how the energy is spread, okay? And I kept thinking there's got to be a better way than simply multiplying by a sequence of plus and minus ones. You just don't have a lot of control how the energy is spread. And I was trying to think if these things I did for the radar could come into play. And here's my last little story. So again, this is a 3D matrix of waveforms, and you think of the third dimension being the waveform stored in this dimension. Okay, and I was thinking, in 301, when we derive discrete time linear convolution, what we do is we represent a discrete time signal sequence as a bunch of time-shifted and scaled Kronecker delta functions. I thought, okay. So let me write that out. And first of all, I thought if I wrote it, it would make people aware that I'm talking about a sequence, not a single number here. This is a sequence if I wrote it this way. Okay, but one day I was driving in the car, and again, we have matrices that satisfy this. Okay, this type of convolution I talked about earlier. Where is that right here? Where pairwise multiplication is replaced by pairwise convolution in the sum here. We have matrices that satisfy this with particularly unimodular sequences. Sequence plus and minus ones, for example. Okay, then when I was driving one day and I said to myself, well, I can replace the Kronecker delta function by the Dirac delta function. And there's a hole, and then everything's a hole, now you have the Dirac delta function here. And then it finally hit me, again driving the car, I said, wait a second, then I can make the independent variable, rather than be time, be frequency, and this holds. Okay, and then what's convolution with the delta function? It slides the spectrum over. And back in time, it's multiplying by a cosine, a sine wave. So I said, oh, okay, so basically, again, given the late hour here, what I was able to do was, instead of multiplying by a sequence of plus and minus ones, multiply by a sum of sine waves that are equally spaced in frequency. The weightings will then be given by the weighting. You still need these matrices to satisfy this property here. Okay, the weightings would be given by those sequences, and I would have this condition here that that now you're just back to regular multiplication here. Because convolution becomes, when I go back from the convolving with the delta function in frequency, bring it back to time, it's multiplying by a sine wave. That essentially, this is a 3D matrix. Every element is a sum of sine waves. And you get this, that they're 0 on the off diagonal. These are, again, three-dimensional matrix. 0's along, coming out of the wall here, and then 1's along the main diagonal coming out of the wall here. And anyway, now, as it stands right now, though, I really haven't accomplished a lot because all the sequences I've designed so far were plus and minus ones. So I'm still putting this roughly the same energy in each band. But like I said, my whole purpose here was to have more control over how the energy was spread. And so, so the only example I have so far for you is this factor where I use these DFT sequences as my weightings on the sine waves. And again, all that's necessary is the frequencies be equally spaced. The channels can be overlapping. And you can use that for spectral shaping, okay, to adjust how the energy is spread. Okay, and here's just an example. I have 4 signals. Actually, to try this out, I took 4 wave files, 4 speech wave files, not even digital signals. And because I just want to show this a generic spreading technique. And I took 4 wave files and I spread them. I just went in digital discrete time world. And I spread them. I broke up the minus pi to plus pi into 4 equally spaced frequency bands. And I spread them. I ran through these 4 different spreadings for 4 different signals. And like I said earlier, once you transmit them from the antenna, they get all mixed up together when they get to the receive antenna. So it doesn't matter if I submit it from different antennas or from the same antenna, they're going to get mixed together anyway. So I just summed them all together and sent them out of a single antenna. This is what it looked like. And yet I could get back any one of them I wanted. This is a single one of them. And I had displaced over here so you could see it was the same. So if you wouldn't see it, it was overlapped. Now you might say, well, the bands don't look like the bands look like they're not overlapping here. Well, that's true because these were oversampled signals, so it's not the big example. I could move the spacing closer rather than pi over 2. But what I did was I want to show that this can be used, if you want to, even in conjunction with spreading. Because you could spread the signal first and then widen up in bandwidth. And I did that in order to show that the bands can be overlapping. So I actually spread them with a direct sequence first, and then ran my algorithm with this multiplied by the sum of sine waves over different time slots. And you got all this. Now they're overlapping, and I could still get back any one individually. Then after this, I had to multiply by the plus and minus ones to get it back to the original one. Okay. Anyway, so it can be used in conjunction with direct sequence if you still really love direct sequence. Okay. I still haven't got to the other issue of how I'm going to adjust the energy, and we'll get there in one moment. So as we move to 5G again, one of our alumni who got his bachelor's, master's, and PhD here, Ted Rappaport, his last year working on his PhD was my first year here at Purdue. And we spent a lot of time together, and we remained friends over the years as he's moved around to different universities. He's a big player in this 5G, and the main thing I'm putting him out is, he believes it's going to happen, that we can do communications at these high frequencies. The issue there is, at those very high frequencies, millimeter wave, because of the atmospheric absorption, the signals don't travel very far if we get too weak. But we can use that to our advantage too, and so now they're talking about having small cells where you have line of sight, picocells, as opposed to larger non-line of sight. So all this great stuff I did when I began my career can be useful now, in particular working for standard beams. And just to give you where we think we're headed here, that they believe, by 2018 we can maybe get 5 gigabits per second links, and then, maybe by some year get it up to that. I guess from Ted, I think. So, and Ted's a dreamer, but so anyway, we showed this picture earlier. Okay, I'm almost done. I had this one novel idea over the summer, and it came from this picture. this was not actually put up by an academic. This was a company that's building these things. And they showed this picture, and it made me think, oh, so now we're going to have multiple beams that could, because you're at massive MIMO, that means large aperture, so that'll mean the beam was narrower. And they're at millimeter wave frequencies, which narrow beam. So now they believe that multiple beams will hit even something as small as a smartphone, or certainly as something like a laptop. And they have this idea, again, of spatial spreading. That is not, what we've done so far in direct sequence spectrum is we take a signal and we spread it across frequency. I said, why don't I take the energy that I'm trying to send something towards a smartphone, let me I think a picture here. Let me take the energy and spread it across beams. It's the same principle. Because remember, I showed you the form of a uniform linear array manifold earlier, and it had the form of a discrete space. It looked like a discrete time sine waves hit with discrete space. So the things we use for beam forming are the same kind of sine waves I used to get these, with those plus and minus, with those sum of sine waves to do frequency spreading. Those same things I can use standard DFT beams to spread energy across multiple beams and collapse them down to a single beam at the end and get a gain equal to the number of beams I spread over. And I know how to do it for not just linear, but for rectangular array. Okay? And so I should probably patent the idea. And you're the first people that are hearing this besides the people that worked on the proposal. I worked on the proposal with David Love and Robert Calderbank, and we're waiting to hear about it. And it encompasses a lot of what we're talking about today. And again, I think that the advantage will be, a better control over how energy is spread. And now I'm talking about spreading energy across not only frequency, across space as well. Okay? And not just in azimuth, but maybe azimuth and elevation beams. I think I have a picture coming up here shortly. And they talk about having analog beams, what are called a Butler matrix beamformer, which is essentially a DFT beamformer for forming analog beams. Oh, my student here, Song, is here. We've already made somewhat of a splash in the massive MIMO world, and I have no time to go into the in any depth. But that's to say that this past December, student Song here in the back row, we got David involved in this work, obviously, as well. We got a best paper award at GLOCOM, and we submitted this paper for a competition in Korea sponsored by Samsung, and he got the silver award for the same work from that. And what was nice was we got academic recognition and industrial recognition for the same piece of work, and that was pretty cool. Here's the spatial spreading idea. I talked about that already. Again, you spread across beams in both azimuth and elevation and collapse it down to a single beam at the end and get a gain. And besides getting a gain, by spreading, and this is what I'll end with this, what I'm talking about is spreading across time, frequency, and space, so you get a product of multiplicative processing gains, and that helps build up the SNR. At the same time, you're being in a very high dimensional space, so again, we hope that it reduces multi-user, what we call access interference. Okay? So there's many benefits to this. Okay, one last thing here. So to do the spreading across space and frequency, I'm not going to go to mathematics, I'm going to gloss over it. I don't need one deglaze. I need two deglaze pairs. Okay? And so I found out, found out that they form, now you're talking about now you're talking about a two-dimensional convolution with a two-dimensional match filter. Two-dimensional convolution, they use two asterisks here. Two-dimensional match filter. And again, if you computed the 2D autocorrelation of this and the 2D autocorrelation, you get a delta function, a two-dimensional delta function. And then I know how to take that and build up higher ones recursively. And these are just some examples. And now at the final, almost done. Now remember what I said was I wanted more control of how I spread the energy. And I realized that if I take something that's already a complementary 2D autocorrelation sequence, 2D autocorrelation pair, a 2D complementary pair, and if I put one by A and one by B, and now take their time reverses and make them and one with a negative sign, multiply that one by A and this one by B, that also forms a complementary pair, but now they won't be plus and minus ones anymore. In particular, if A and B are both equal to 0.5, you'd have either 1, 0, minus 1. I start to have zeros, which will allow me to, if there's a band because of either multi-phase propagation or due to atmospheric absorption, was a band I shouldn't be putting any energy in, I'll have a 0 there. So just give you an idea that I have designs now where I not just put ones and minus ones, but other things I can do to how to distribute the energy. Okay. And I think that's enough. This is the second last slide here. I certainly love teaching here. I've been honored to get a couple teaching awards. It seems like one per decade. And the most recent one was the distance education award. I was quite surprised by that. I was happy to get that. I've graduated 31 PhD students. Number 31 is sitting in the back there, Ali, and 32 will be Song pretty soon. And again, I'll end with that I was massive MIMO before massive MIMO was cool. So, thank you.